That doesn't apply to you. What?
My usual peanut butter and cream cheese. Because it gives me protein that gets me through a couple hours. All that. You'll give me your yellow pages. Click on the grade tab after you can, and then click on review, and it will tell you which ones you got wrong. Gradebook? Yeah, gradebook tab. Yeah, gradebook tab. There's a little link review right next to it. Yeah.
I can get
What you need to do is rework the ones that are marked incorrect with the X, turn those into me on separate paper by a week from today. And then what I do is I look at this, so I take this, I look at this, and here, what's your last name on that? I look at this, and then I see what partial credit you can get on your work pages. But I want you to rework the problem, because a lot of this stuff turns up again on the final.
Okay.
Oh.
What is that on that?
Okay. Yeah. Just plug it into whichever part. Just try to find a plug for that. Nothing to do with you guys. If you would, though, here's where you can turn in the homework number 4. And if you need it, here's a stapler. Okay. We're going to get started. Be sure you turn in homework number 4. And I also have made available at your schools homework number 5 that you should, by the end of the class, be getting a copy of. And that's due a week from today. And I think that's on section 7.3 and 7.4. Today we will be finishing up 7.4 on partial fractions. Also, all of these homework assignments can be printed right off of a blackboard in case the dog throws up on your copy or something like that. In my case, in case one of my cats has a hairball right in the middle of it or something like that. All right. So 7.4, we had gotten started on this the other day, and it's basically using what are called partial fractions to help integrate things that normally we wouldn't even know how to integrate. We're talking about a polynomial over a polynomial, and we're talking about the degree of the top one is less than the degree of the bottom one. Is less than the degree of the bottom one. All right. Now, and that's a very important point, that the degree of the top is less. We had started with this example of trying to integrate this polynomial over a polynomial. And by the way, the official term for that is a rational expression. Okay? We had x squared plus 2x minus 1 all over 2x to the third plus 3x squared minus 2x dx. All right. And so just looking at that offhand, you'd be hard-pressed any kind of substitution or anything to do this. What we first want to do is fully factor the denominator. And I'm not going to go through that whole process, but we're going to have x squared plus 2x minus 1 all over x times 2x minus 1 times x plus 2. All right. As I said, most likely, for the most part on exams, they'll be factored, except for obvious things like a difference of 2 squares. You all ought to know how to factor something like that. Okay? Difference of 2 squares. Jenna? All right. Now, what we do with this, and notice here we have 1, 2, 3 factors here. We're going to divide it up into 3 fractions. So each denominator is going to have one of the factors. So I have a over x, that's our first factor.
b over 2x minus 1 plus a c over the x plus 2. Okay, we're going to be breaking this thing up. Notice also that the degree of the top is smaller than the degree of the bottom. Yes?
Okay, so you know how it's on the left side that stuff is on the bottom? Once you multiply it over, shouldn't it be on the top?
It will be. That's our next step. Okay, the next step we're going to do is multiply everything by all the factors that are here on the bottom. Basically, by doing that, we're going to get rid of the denominators when we do that. So we're going to multiply all terms on both sides by x times 2x minus 1 times x plus 2. That's called the least common denominator. All right, so when we do that, the left-hand side becomes x squared plus 2x minus 1. We no longer have a denominator there. And on the right side, we have a, and then we are going to be multiplying it by the two factors that will be left over when we multiply by our least common denominator. That would be the 2x minus 1 and the x plus 2. Then we have plus b, and again multiplying it by the two factors that would be left over. When we multiply, that would be the x and times the x plus 2. And then finally the c plus c, and the two factors that would be left over would be x and 2x minus 1. All right. So we don't have any more denominators, which is exactly what you were saying. And of course, what are we trying to do here? We're trying to solve for the numbers a, b, and c. That's what we're trying to do. I want to point this out here. Okay, the degree of this is less than the degree of our denominator here. Here, the degree of our denominators are all 1. Degree equals 1. So what we put on top here are just constants. Because constants actually have a degree, and its degree equal to 0. That's what a constant has. All right, now to solve for, so we have this equation right here. So this equation is supposed to be, will be valid for all values of x. All right, this is an equation. So there's a nice, easy way to do this to solve for a, b, and c. What I do is pick numbers that'll cause one or more of my terms on the right side to equal 0. Pick numbers that will cause one or more of the right-hand terms to become 0. All right, so let's look here. If I pick, say, x equal to 0, let x equal to 0. That's going to cause the second term here to be 0 because I'm multiplying by x. That'll also cause this third term to be 0 because I'm multiplying by x. Does everybody see that? That those last two terms would zero out with that particular selection of x. So what I have here then, I plug in 0 for x. So on the right-hand side, I'm going to have 0 squared plus 2 times 0 minus 1. So I'm just going to have minus 1 on the left-hand side. Now on the right-hand side, I don't have to worry about those last two terms. They're going to just end up being 0. So I plug in 0 for x here with that first term. So that's going to be a times 0 minus 1 is a negative 1 times 0 plus 2, which is a 2. So automatically then I have this equation that minus 2 times a equals negative 1. Nice. So now I can solve for a, and A is going to equal the number 1 over 2, 1/2. And you know what I'm going to do right up here is right up here where I had broken them apart, I'm going to write 1/2 up there also, just to show that that's what my A value is. Okay, now let's get what other value of X, what's another value of X that I can pick that's going to cause some of these terms over here to zero out? 1/2? Yep, 1/2 will. If I pick 1/2, 2 times 1/2 minus 1 is 1 minus 1. That'll zero that term out, and it'll also zero my last term out. So 1/2 is another good number. So let X equal 1/2. All right, so the only problem with 1/2 that we just have to grin and bear it is we have to do a little fraction manipulation here on the left-hand side. Okay, so we have to plug in 1/2. So we have X squared, that's going to be 1/2 squared, that's 1/4. Plus 2X, that'll be 2 times 1/2, that's 1. And then minus 1. So that's the left-hand side. Equals, okay, the first term will become 0 because X equals 1/2. Now the second term won't, so I have to plug in here. B times X. Well, X I'm going to plug in 1/2, and then I have 1/2 plus 2. Well, 1/2 plus 2 is 2.5. Let me convert it into an improper fraction. That's 5/2. And then my last term will go to 0 because of the choice of 1/2. So let's see what we get with this. Okay, the 1's cancel out on the left side, so I still have a 1/4 there. And then on the right side, I have 5 times 4, 5 over 4 rather, times B. So now I solve for B by just simple algebra, multiplying both sides by 4/5, the reciprocal. So B is equal to 4/5 times 1/4, or 1 over 5. So I've solved for B. And I'm going to mark it up there also that I solved for B. Okay, so the other one that I need to solve for then is C. What other number can I pick that's going to cause some of these terms up here to be 0? -2, because I have an X plus 2 and an X plus 2. If I make X equal to -2, those will become 0. So finally, let X equal -2. All right. Okay, so I have to plug in on the left side, and be careful because it's a negative number. -2 squared is +4, not -4. 2 times -2 is -4, and then I have a -1. All right. Now this first term will disappear because of the -2. The second term will also be 0 because of the -2. So this is the term that I'm left with. C times -2 for the X times, let's see, 2 times -2 is -4, -4 minus 1 is a -5. All right. So what do I have here? The 4's cancel out, so I have -1 equals, well, -2 times -5 is a +10, 10 times C. Divide by 10, and I find that C is equal to -1/10. So I have my third and last letter solved for. Before I go on to the integrals themselves, any question about how this is a nice way that you can usually, but not always, use for these to get these A, B, and C. Okay, so let's see what this has given us then. This has given us then that our original, let's write down our original X squared plus 2X minus 1 over, and I'll even write it down as our, well here, X times 2X minus 1 over X plus 2. This now can be rewritten as the following. 1/2 over X plus 1 over 5. 1/5 over 2x minus 1 minus 1/10 over x plus 2. So I have three nice things that it's equal to. So we want to, of course, the whole point was to integrate these with respect to x. All right. Each one of these is nice to do. This first one, 1/2 over x, is going to become 1/2 times the ln of the absolute value of x. This, by this time, should be something you can get right away. The second one, I do have to use a u substitution if I need to let u equal to 2x minus 1. And then my du equals 2 times dx. And so therefore, by dividing by 2, I have that dx is 1/2 times du. So this then becomes, let me put it down here, is 1/5 over u times 1/2 du. That's how it converts with doing the u substitution. So basically, this is going to become what? 1/2 times 1/5 is 1/10 ln of the absolute value of u, but then that's really, when we back substitute, that's really 1/10 times the absolute value of 2x minus 1. Okay. So that's our second one. Let me carry down our first one. 1/2 ln of the absolute value of x. And then we go on to the last term that we created, and that's another easy one. That's minus 1/10, and that'll just be the ln of x plus absolute value of x plus 2. And then we tack on our plus c, and we're finished. So something that looked impossible to do, converted into three integrals that are fairly easy to do. And that's the whole key behind this process. Question on this example, first of all. Yes, Jordan.
How can we just use the second one and not the third?
Well, I mean, I could have done a u substitution for that. So why didn't I do a u substitution for the third one? Okay, let's just see what will happen when I do that. If I let u equal the x plus 2, then Jordan, what would du be if I let u equal x plus 2? 1 times dx, right? Right. So therefore, this substitutes to minus 1/10 du all over u, right? Which is minus 1/10 the ln of absolute value of u. When your coefficient in front of your x is a nice 1 like this, and it's just like x plus something or x minus something, you don't really have to go through that whole u substitution business. I mean, you can, and hopefully you'll get to the right answer. You just don't have to. All right. Does that answer your question? All right. Okay. Let's look at a second example. And this one is where we have the difference of two squares. So we're doing the integral of dx divided by x squared minus 4. All right. Now, it is true that we could use some kind of trig substitution to obtain the answer. All right. I mean, that's a possibility. If I were going to do a trig substitution, what would I let my x be equal to? My x is in front of the minus sign. If I were going to do that. Anybody? Nobody is coming up with anything. Secant, right. I could use x equal to 2 secant theta, but I'm not going to. We're going to do partial fractions with this. All right. So we have this thing. Let's just write it like this. We have 1 over x squared minus 4, And let's fully factor this. Well, this is the difference of two squares. I certainly expect you guys to be able to factor this. This is x plus 2 times x minus 2. So you have to fully factor the denominator. Occasionally, you might find yourself having to do that. All right. So we have two separate factors. They're both what are called linear factors, just like before. These are called linear, L-I-N-E-A-R factors. And then, so I'll divide this up, a over the first factor, x plus 2, plus b over the second factor, x minus 2. All right, and we're going to solve for a and b. Okay, so again, I multiply everything on both sides by the factor denominator, x plus 2 times x minus 2. Multiply by x plus 2 times x minus 2, everything. So the left side, of course, just becomes a 1. Now the right side is going to be this a times the other factor, which will be left over, x minus 2, and plus b then times the other factor that's left over, x plus 2. Just like that. All right. Now, we want to try to do it the easy, faster way. So let's choose x to be a couple of numbers that will zero out one of these terms when I do that. So let me pick x equals 2 for starters. That'll cause 2 minus 2. That first term will be 0. So I'll have 1 equals, that's a 0, b times 2 plus 2, b times 4. So b is equal to 1/4. Now let's go over and let's pick another value for x. How about minus 2? Minus 2 will cause this second term to become 0. So now I'll have 1 equals a minus 2 is a negative 4, and the other term is 0. So solving for a, I get that a is equal to a negative 1/4. So here I have for a negative 1/4, and for b I have positive 1/4. All right. So let's do these integrals here. Integral of minus 1/4 over the x plus 2 plus 1 over 4 over the x minus 2 dx. Now, Jordan, here's another case where you can certainly let u equal x plus 2 or x minus 2, but you'll find out, you know, it's kind of like a lot of work for nothing. I mean, you will do that, but what are we going to get here for the antiderivative of the first term?
Negative 1/4 ln of x.
Right. For the first one, we're going to get a minus 1/4 times the ln of the absolute value of x plus 2. And then for the second one, we get a plus 1/4 times the ln of the absolute value of x minus 2, and plus c then. Finished. Something that looked hard becomes easier. All right. Now we're going to up the ante a little bit, because you know that's what we do in math, right? We start easier and then get a little bit harder. Anyway, let's look at this one. 4x on the top, and on the bottom, I've got it already fully factored, so that's good. X minus 1, but that one's squared, times x plus 1, dx. All right. Now what this is a case where one of our linear factors occurs more than once. This linear factor, the first one, this linear factor, in this case, occurs twice, more than once. All right. Now what we do is this. We now have to add an additional fraction on the right-hand side that has the increasing power, that has increasing powers of this factor. So let me just put this, what we're going to have, and then I'll put some English below it. We're going to have, here's our factor, x minus 1, but it occurs twice. So we're going to have, first of all, our letter A over just the x minus 1. But it occurs twice. It's a squared. So we have to have a second one, but this one is going to be over x minus 1 in parentheses squared. Yep, we have to do that. And then I have my third factor, which only occurs once, so I'll have a c over the x plus 1 for that one. So let me put down here more formally what we have to do. We add additional quote-unquote fractions on the right that have quote-unquote increasing powers of the factor. Okay. Yes?
Why do we do that though?
Because it won't work if we don't. I'm just going to answer it like that. It won't work if we don't. There's actually a formal theory behind this. All right? The big theorem in algebra behind partial fractions. All I'm going to tell you is it won't work if you don't do it. I'm just going to give you that flat-out answer. Okay? So it has to be that way. All right. I have a recommendation for you. Try to do this, not during class. Try to do this without having that middle term. See what you get by trying just the first and the third term, and that should present you with your answer. Because you're going to find that somewhere along the way you get stuck. Okay? I know that may not seem like a good answer. It's like because I told you so kind of answer, but that is basically what we're talking about. That's how you have to do it. Okay, we do the same thing then. We multiply both sides by all of those factors. All right. Multiply both sides by, let's see, we're going to multiply by x minus 1 squared times x plus 1, that whole factoring of that denominator. So this is what we're going to get then. On the left side, we're just going to come up with the 4x when we do that. On the right side, let's see that a, now I'm multiplying by x minus 1 squared. So I'm going to lose one of the x minus 1s when I do this, but I'm still going to have another x minus 1 left over. And then I also have the x plus 1 that hasn't been canceled out either. So that's what I have after my a. Now, with my b, both of the x minus 1 squares will cancel out. So all I will have left over as a factor is the x plus 1. Does everybody see that? How that's, you just look at what's left. What doesn't cancel out is what I put there behind that. And then for the c, the x plus 1 will cancel out, but both the x minus 1s won't. So I'm going to have c times x minus 1 squared behind the c. All right? Okay. And then let's do this process again and see what happens. Let's try the easy way. Let's pick a value for x that will zero something out on the right-hand side. 1. 1 will work. Let x equal 1. Okay. So on the left side, it's 4 times 1, so that's a 4. Now this all will become 0 because 1 minus 1 is 0. The third one will become 0 also. My middle one won't. I'm going to have b times 1 plus 1, or 2. So 4 is equal to 2 times b, so b is equal to 4 over 2. b is equal to 2. So I'll go up here. I mean, you don't have to go up there and pencil that in, but I'm going to do that. So we have our b. And we're going to have another hopefully obvious value for x that we can use. What would be another value for x that'll zero things out? Negative 1. So let x equal negative 1. Now on the left-hand side, that's going to be 4 times minus 1, so that's a negative 4 on the left. Okay, with negative 1, my first term will zero out because I have x plus 1. With negative 1, my second term zeroes out again. I have my third term, c. Now let's see, that's negative 1 minus 1, that's negative 2, and then I square it, so I have 4, positive 4. All right? So be careful with the arithmetic. So therefore, when I solve for c, then I'm going to get c is dividing by 4, I get c is equal to minus 1. All right. So let me plug in that up there. All right. We still have to solve for a. Now the thing is, we've run out of magic numbers that'll just zero things out. All right. There's still a possibility here, and this is the possibility. Basically, there's two things we could do. One of two ways we can go with this. One is we could pick another number that's not going to zero everything out, but will still give us some kind of an equation that we could use. We don't want it to be a real big number because we don't want to do a lot of terrible arithmetic. I'm just saying, well, let's see what happens if we let x equal 0, say. Okay. Now then, on the left side, we have 4 times x. So if x is 0, our left side is just going to be 0. Now on the right side here, we're going to have 0 minus 1. We'll have a times negative 1, 0 minus 1, times 0 plus 1, or 1. So we have that, plus b times 0 plus 1, which is going to be a 1, plus c times, now 0 minus 1 is negative 1, but negative 1 squared is a positive 1, so I have a 1 there. So what I have here basically is 0 is equal to, let's see, that first term becomes a negative a plus b plus c. Okay, so what do we still have to solve for? We've solved for b, we've solved for c, we haven't solved for a yet. But this other number has given me a relationship of a with the other two values. What can I do here? If I add a to both sides, I get that a is equal to b plus c. I already know b, I already know c, so I'll get a right now. So b was what? B was 2, c was a negative 1, so by combining those two, I get that a is equal to 1, 2 minus 1. So I have solved for a now. All right, without going through too much algebra stuff. Now, I want to point out another way I could have gotten this, because we're going to pretty much have to use this other way for some of the examples that you're going to have today. What I can do here is, let's go way back up here to this equation that I got when I had multiplied everything by the denominator. And let us FOIL stuff out on the right-hand side. So I have 4x equals a. Now, FOILing x minus 1 times x plus 1, I'm going to get x squared minus 1 when I FOIL that out. Then let's go to the second one. Well, the second one is just b times x plus 1. And now the third one, when I multiply x minus 1 by x minus 1, I get x squared minus 2x plus 1. All right. And that all needs to equal 4x on the left-hand side. Now, let me just distribute this for a minute then. So we have a times x squared minus 1 times a minus a plus distribute here b times x plus b and distribute the c plus c times x squared minus 2 times c times x plus c times 1c. All right. Now, is there any x squared over on the left-hand side? No, no x squared. So actually, you could say there's a 0x squared on the left-hand side. So what we do here is we equate the coefficients of the x squares to get a relationship. So equate the coefficients of the x squares. All right, so I'm running out of room now. Well, let's see here. On the left-hand side, we had already said the coefficient is really a 0. On the right-hand side, we have a plus c. Those are the only two, a plus c. So what this is another way of obtaining other values. So I know that a plus c must equal 0 by equating those coefficients of the x squared. Does everybody see how I got this a plus c on the right-hand side? I've got an x squared here and an x squared there. Both, so I just add up their coefficients. So therefore I know that, let's see, we're looking for a, that a has to equal negative c. All right. Now, let's see, I think we already, we already found c. Remember, c is equal to negative 1. We found that up above. So therefore, a is the opposite, so therefore a is equal to 1. It's another way to do it, all right? So so now we have our 3 values. So let me go back up here then. So this is what we started with. Integral of 4x over x minus 1 squared times x plus 1 dx. And now, with the partial fractions, this is equal to the antiderivative. Let's see, the a was a 1 over x minus 1. The b was a 2 plus 2 over x minus 1 squared. And the c was a minus 1 over x plus 1 dx. So we now have 3 terms, and we can integrate all of those terms. The first term, without having to do a u substitution, is just going to be the natural log of the absolute value of x minus 1. Now the second one, if we look at u equaling x minus 1 here for the second one, the second term here is 2 over u squared, which is equal to 2 times u to the negative 2 power. So to get the antiderivative of, and our du is equal to dx. All right. Now I know a lot of you wouldn't have to go through this whole formal process for this, but our antiderivative of 2 times u to the minus 2 is 2 times u to the minus 1 over minus 1. All right? And then we plug in what our u is. So we get 2 over minus 1 is minus 2, and then our u is x minus 1 to the minus 1 power. Or we could have just put the x minus 1 in the denominator. Either way. So here's our first 2 terms. We okay with that second one, just doing a basic substitution. And then our third one is another natural log. Now notice it's a minus natural log. This time it's the absolute value of x plus 1 and plus c. So we end up with 3 fairly easy antiderivatives to get. by doing the partial fraction. Okay. All right. Question on that one? Hopefully, if you've never been exposed to this before, and some of you, Kyle, have you been exposed to this before? Okay, because I'm gathering you probably have. All right. Okay. Let's do another example here. Let's see what else. Now, how else can we up the ante with this? So far, all of our factors in the denominator have been linear factors, like x plus 1, 2x minus 1. Those are called linear factors. What happens if we can't factor it into all linear factors? Because you know from algebra, at least I hope you did know, that when you factor something, sometimes you can't factor it into all linear factors, all right? So let's see here. So this is our scenario right here. What if we can't get all linear factors? Okay. So here's the example that I want to show. Integral of x over x minus 2 times x squared plus 4 dx. Now, x squared plus 4, with real numbers, I cannot factor that any further. If it were x squared minus 4, it would be the difference of two squares. But it's not. It's x squared plus 4. I want to point this out to you guys. Fact. This, by the way, this is called a quadratic factor because it has a power of 2. Quadratic factor. Fact. If a quadratic factor, and I'm going to put the general form of it that a quadratic factor would have. Some number a times x squared plus some number b times x plus some number c. If a quadratic factor that has that form, actually, I really want to get rid of that if. Let's get rid, because this thing won't sound right otherwise. A quadratic factor will not be further factorable, or further factorable, I guess, if b squared minus 4ac is less than 0. Now that term b squared minus 4ac you should remember from the quadratic formula. What happens, that's what's under the square root radical. What happens when that's less than 0, you end up with two complex numbers with the I. Okay, remember that? Square root of a negative number, you have I as part of your answer. So if we have a quadratic factor where the b squared minus the 4ac is less than 0, then we're not going to be able to, you just give up, you can't factor it any further. Now in this case, let's just look at what we have. We have a is equal to the number 1. In this case, there is no x term, so b is equal to 0, and c is equal to 4. So b squared minus 4ac is equal to negative 16, right? Right. And so it's not going to be further factorable. All right. So what do we do here when one of our terms can't be broken up, factors can't be broken up anymore? All right. There's still hope, but we have to write it differently. So here we're dealing with x over x minus 2 times x squared plus 4. All right. We still have a linear term here, x minus 2. So I'm still just going to put an a over that linear term, x minus 2. But for this other one that I cannot further factor, let me put that in the denominator, x squared plus 4. Now I have to put a linear term above it. So I'm going to put an b times x plus c. I have to put, this is a degree 1 linear term that I have to put over my quadratic. This is a degree 2. All right. And we have to do that because that's how the theorem shows that we have to do this. So this makes things a little bit more complicated when we break it up. Does anybody see that, I mean, not why, but how, if I have an unbreakable quadratic here, I then have to put like a bx plus c on top of it. All right? All right, we again multiply by everything by the terms in the denominator, or by the factors. So we multiply, just like before, by x minus 2 times x squared plus 4. That doesn't change. Multiply by that. So when we do that, the left side just becomes plain old x. Now let's look at what happens here on the right side. The x minus 2's are going to cancel out. I'm still left with an x squared plus 4. So I'm going to have a times x squared plus 4. All right? Now for the second one, plus, I've got bx plus c. Let me put that in parentheses. What I'm going to have left over when I multiply by x minus 2 times x squared plus 4, I'm going to have left over an x minus 2. So that's our new equation with no denominators. You okay with that? Right? Okay. All right. Now, we, of course, again, we need to solve. Oh, we need to solve, as before, for a, b, and c. All right. Okay, well, one thing that comes into play is there's at least one number we can use. Oh, right, we can use the 2, right? The 2 here will work. So let x equal 2. That'll help us, because that'll zero out that second term. So be sure you, any place there's an x, be sure you plug it in with your number. So on the left side, I'm going to have a 2 equals a times what? Well, 2 squared plus 4. That's 4 plus 4, that's 8. And my second term will be a 0. So I can solve for 8 at least. I have 8a is equal to 2. So dividing by 8, I get that a is equal to 1/4. Okay, well, I've gotten that at least. Now, unfortunately, for b and c, I don't have anything that's obvious that I can use. So this is what I'm recommending that you do here. You basically FOIL things out and equate the coefficients. That's what I recommend that you do. Although, you certainly could, say, pick another number like, say, 0 and work with that and see what kind of relationship you get. I mean, you could do it that way. But I'm just going to want to, right now, just go with the equating the coefficients. So let's see here. X equals, let me distribute that a. So it's ax squared plus 4 times a. And then let me FOIL bx plus c times x minus 2. That's going to give me bx squared minus 2bx plus cx minus 2c when I FOIL that out. All right. Okay. Now notice here on the left, we just have an x coefficient. We have no x squared, and also we have no constant term. We just have an x. All right. So one thing can somebody tell me what I might want to do here to solve for another one of the letters? What I can equate with what?
What's your x squared?
Well, what's that now, plus 0?
Don't you add, you need to add a plus 0x squared.
Yeah, right. That's exactly right. You can act as if we have a 0 times x squared on the left-hand side. So then, with that said, Jordan, what can I equate between the left side and the right side?
0 equals a plus b.
Yeah, exactly. 0 equals a plus b. Jenna, was that what you were going to indicate also? All right. So we can equate the x, and this is how I kind of write it when I do these problems myself. I write the x squared, I put a colon or something like that there, and then after it I put my equation that I get. 0 has to equal a plus b. Because those are the only two terms on the right that have an x squared. Everything else either is a constant or just has the x. So we just equate the coefficients of the x squared. Let me write that down. Equate the coefficients of the x squared. All right. So therefore we know that if a plus b is equal to 0, well, we know that b, if I subtract a from both sides, b has to equal negative a. Well, we already found a just a couple minutes ago. A is 1/4, so b is minus 1/4. So we've gotten 2/3 of the way through. We now have b. All right. Let's see what else we can do here. Anybody have any other ideas of what we can do here? Because we still have to solve for c. And I want you to look at that boiling out thing that I've got there and see what we might be able to use as an equation to get c. Is there any, let's see. What do we have as an x term over, here we have a 1 times x, right? 1 times x? What do I have for x terms, just x terms over here? What are the coefficients that I have that just have the x behind them? Yeah, I've got a negative 2b here, that's with the x. And I have a plus c, that's with the x also. So those combinations have to equal my 1 on the other side. So here, I'm just going to put an x here with a colon to indicate I'm working with x. So 1 on the left side has to equal the sum of my coefficients of x on the right side. So 1 has to equal negative 2b plus c. All right. Let's see. Well, hey, we just found out what b was. So let's plug in that, and we'll be able to solve for c. So 1 is equal to minus 2 times, let's see, b was negative 1/4 plus c. All right. So what do we have? 1 is equal to negative 2 times minus 1/4, that's a positive 1/2, plus c. Subtract 1/2, we find that c is equal to 1/2. So now we have all of them. So when we have these quadratic factors, it's a little bit more work getting the a, b, and c. So my c is 1/2. All right, so let's just do the integration here then. Let's rewrite what we have. Okay, so my integral of x over x minus 2 times x squared plus 4 dx can be rewritten then as the following: 1/4 over x minus 2 plus minus 1/4 x plus 1/2 over x squared plus 4 dx. All right. All right, let's see what we can do. Yes, Jenna?
I think c is 3.
Hmm?
I think c is 3.
Let's see here. Okay, let's go back here. Okay. Okay, we agree that 1 has to equal negative 2b plus c. Okay. And what did we come up with for b? We have, we have a negative 2 times a negative 1/4. That gives us a positive value, double negative. So that gives us a positive 1/2, positive 1/2. And when we subtract 1/2 from both sides, we're going to get 1 minus 1/2. All right, we're going to get 1/2. So I think you had a minus sign going wrong there. All right. All right. Okay, now the first term on this should be easy to do. 1/4 over x minus 2. That's just going to give us what? 1/4 times the ln of the absolute value of x minus 2 without doing any kind of special use substitution. The second one, what are we going to do with the second term here? Any thoughts on what might be a strategy for the second term? Running out of strategies?
We make it 2 different fractions.
Yeah, exactly. That's the strategy. Break it up into 2. We have 2 terms in the numerator. Let's break it up. If we have 2 things in the numerator, we can have one fraction with one of the terms, the other fraction with the other term. So I can write this as minus 1/4 x over my denominator plus 1/2 over my denominator. Okay? And that's the key. And that's a technique that you'll be doing with more than one problem to help you get the antiderivative. So that's something to always look for, breaking that up. Now, with that done, what technique then can I use for the first one, minus 1/4 x over x squared plus 4, to get an antiderivative? Can I do a substitution? Can somebody give me the substitution?
You know what?
Yeah, let u equal x squared plus 4. Because when I get the du, my du is going to equal 2x times dx. And then all I need to do is multiply to get my minus 1/4 that I have up above. So what I want to do is I want to convert this 2x dx into a minus 1/4. So if you think about it, if you multiply both sides by negative 1/8, negative 1/8 times 2x dx, I'll get minus 1/8 du is equal to the minus 1/4x dx that is in my integral. All right? So my substitution then becomes this, minus 1/8 du, and then I have 1/u in my denominator. Everybody okay with that? So we get an ln. Minus 1/8 times the ln of the absolute value of u. I'll leave the plus c for later. And then we just back substitute the u. Minus 1/8 times the ln of, now the u way back up here is x squared plus 4. Okay? So a u substitution saves the day with that one. Okay, so we okay with that middle one? Now, then we still have one more to go, this one right here. Now, I'm going to tell you, I think this is a formula that we mentioned before, but if not, I want to put it up here before we even do it. And I'm putting my good asterisk by it, which we all know what that means. The antiderivative of dx over x squared plus a squared, so this is the formula, is equal to the following. 1/a times the tan inverse of x over a. And this is obtained by doing it, letting x equal a times the tangent of theta. That's obtained by doing that kind of a substitution. But what I want you guys to do is to memorize or to remember this formula rather than having to go through the whole process of doing a trig substitution to derive it. Okay? It's easier just to have it up here rather than to go through the whole process of deriving it. So with that said, let's look at the final one that we need to get here. Okay, the only thing we have an x squared plus 4, so our a is equal to 2, right? 2 squared. And we can't forget the 1/2. That's got to be carried as a coefficient in front. So what is this going to be? This is going to be plus, I'm carrying down my 1/2. Now, let's see what this is going to be. This 1 over x squared plus 4, okay, it's going to be 1 over a, so that's 1 over 2, 1 over a, times the tan inverse of x over a, but it'll be x over 2. Right, just using the formula right here. But I have an additional 1/2 in front of it. So, this then, just to clean this up a little bit, this becomes 1 over 4, 1/2 times 1/2, times the tan inverse of x over 2, and now I'll tack on my constant c. Okay? So, I really want you guys to get this particular formula down there. Okay. With that, I think we need a 5-minute break. All right. Okay. So. Huh?
One problem, like age and
Yeah, these things can be lengthy. So I got 6 after on my watch. So 11 after, we'll resume. If you want to get up and move around or do something. Again, don't forget the homework. You've got the new homework.
I only got the first section of the homework done, so I'm just SOL on the second part. There's no, like, turn it in Monday or anything.
You can turn it in late. I'll take a 20 something off. Go on. I want you to do the problem.
I want to do the homework,
You need
but
it,
I have a hard time making myself do it for nothing. Kind of.
Yeah, I hear you. No, go on and turn it in. Yeah. It won't be for nothing. work on the next one. Already. Already. All right. I saw you working there. I thought, that would be actually that would be like obviously you get things as soon as you get them, you start working on them. So I can't do that. I can't wait. That is so wrong. That is so wrong. Get that black cloud over your head. Get it over with. Yeah. Yeah, procrastinate, do it like 2 hours before like midnight. Because that's the only way you operate, right? Only way you operate under pressure.
Because it's very
But, huh? You just have, but that really is a lot of pressure. Because what if all of a sudden you're 2 hours ahead, there you are, and you realize, man, I really need to ask somebody about this. I don't know what the heck's going on.
I'm pretty good with judging the amount of time.
You are, huh? All right. Good.
I started studying like at 8, went all the way to,
Okay.
8 o'clock all the way to 1 a.m. and then I woke up 5 hours later.
Okay. All right. Well, you know what's best for you. Okay. All right. We're gonna start up again, folks. This next one, it ups the ante even more, and I'm only going to work part of the problem because otherwise it would be the entire rest of the class. All right?
Wait, what? Wait.
45 minutes for one problem?
Probably. Why would I have you do that? Because I'm a mean person? You know that I'm a math teacher. All right. Never mind. Here we have, this is x squared plus 1 over x minus 1. And guess what we now have? We have one of those unfactorable terms, but now it occurs twice. So the unfactorable term is now occurring twice. So this is your dx. This is your worst case scenario, all right? So basically, we want to divide this up into partial fractions. Again, the degree of the top is less than the degree of the bottom, so we always have to check for that. So we're going to have a over my nice linear term, a over x minus 1. But now I'm going to have 2 more terms here. I'm going to have a bx plus c over x squared plus 4. But then I need a plus, let's see, abc dx plus e, another linear term, over the square of the quadratic there, because it goes up to a power of 2. And of course, we multiply both sides by, of course, the x minus 1 times the x squared plus 4 squared in order to get rid of our denominators. So what we end up with on the left side is, of course, just the numerator, x squared plus 1. Over on the other side, let's see. Well, we won't have an x minus 1 will cancel out here, but I still have the x squared plus 4, and it occurs twice. So that's going to be a square there after the a. Plus, now I have this bx plus c. One of the x squared plus 4s will cancel out. I still have an x minus 1, and I still have one of the x squared plus 4s. Yes?
Okay, so when you're multiplying, you don't multiply by x squared plus 4 squared?
I do. Mm-hmm.
Then wouldn't it be x squared plus 4 to the third?
What? What? No, that x squared plus 4 is in the denominator.
So you're multiplying it by both of them, so that's 3 of them.
No, oh, no. What I'm doing here is I'm multiplying this everything. So in other words, Jenna, over here, I would be multiplying this by x minus 1 times x squared plus 4 squared. That's what I'm multiplying all of my terms by. There's something that cancels out here, not adds to it. No, I see what you're saying, no. My denominator here is x minus 1 times x squared plus 4 times x squared plus 4. That's all that I'm going to multiply everything by. I'm not going to be multiplying by another factor of x squared plus 4. Is that what you're thinking?
Yes.
All right, okay. And then plus, then let's get the last term, dx plus e. Now, in this case, both of the x squared plus 4s will cancel out, but I'll still be left with an x minus 1. All right. Now, certainly I can use an x equal 1 to get one of the numbers. Basically, the process that I had to do here on the paper was to FOIL everything out on the right-hand side for the most part. I can let x equal 1 to if I let x equal 1, I'll find that a is equal to what? 2 over 25. Because this will zero out, this will zero out, and I just fill in my 1 here. So I'll get a equals 2 over 25. But after that, I want to just FOIL everything out and equate the coefficients of each of the powers of x. So I just basically multiplied the left side out and then equated the coefficients for each of the powers of x. All right. And that includes the constant term. All right. What I ended up getting was this, because this is what would take the rest of the time. I get this as I get 2 over 25 over x minus 1. That's my a that I already got. And then minus 2 over 25 times x, that's my b. And my c is also minus 2 over 25. And that's over the x squared plus 4. And then plus my d and my e, they're both 3/5. 3/5 x plus 3/5 all over x squared plus 4 in parentheses squared. So this is what I get. This was my a, this is my b, this is my c, that's my d, and that's my e that I come up with. All right. Let me write this a little bit simpler here before we do integrating. What's that? Yeah, the d and e are both equal to 3/5. So that's 3 over 5 times x plus 3 over 5. So notice they're both 2 over 25 here. So let me draw out a minus 2 over 25. And I have an x plus 1 left over x squared plus 4. And notice I have a 3/5 in both of those terms. So I'm going to draw a 3/5 out. And I'm left with an x plus 1 over x squared plus 4 in parentheses squared. All right. The first one's easy to get, I hope. 2 over 25 times the natural log of x minus 1. Now, for the second and the third terms, I need to do what Will had suggested that we do before. I need to break up, in order to get these antiderivatives, I need to break, notice there are two terms in the numerator here. There's an x, there's a 1, there's an x, there's a 1. I need to break these up into two terms, all right, to get the antiderivative. And I'm not going to go through the whole process here. For this first one, I'm going to have x over x squared plus 4. So I'm going to use a u substitution like we did a few minutes ago. Let u equal x squared plus 4. And I can finish my u substitution. For the second one, I have 1 over x squared plus 4 for my second term. I'm going to use that formula that I just gave for that tan inverse. That formula right up here that I gave you guys, 1 over x squared plus a squared. So this is going to be, now here my a again is the number 2, so it's going to be 1 over a, 1 over 2, tan inverse of x over a, x over 2. Yes?
You multiply by...
Yes, absolutely. I'm omitting for just simplicity, just for this minus 2 over 25 absolutely has to be multiplied in. I can't forget that. That's in front. Thank you. And, all right. Now, for this last one, again, I divide this up into 2. The first one is going to be x over x squared plus 4, and that's squared. And again, I can do a u substitution for this. I again let u equal the x squared plus 4. All right? And I get my u substitution that way. All right. And that's going to give us, when I also factor in the 3/5, that's going to give me a result of minus 3 over 10 times x squared plus 4 to the minus 1 power. All right. Okay. Then we have, last but not least, we have the second part of this one. This is 1 over x squared plus 4 squared dx. And of course, it's multiplied by 3/5 also. I need to mention that. All right. Now, I've gotten the antiderivative of this, but I'm going to give you this as a take-home assignment. So alert, take-home assignment. It's worth 10 points. Okay, and it's this. Show that the antiderivative of 1 over x squared plus 4 in parentheses squared dx is equal to the following. 1 over 16 tan inverse of x over 2 plus 1 over 8 times x over x squared plus 4. That's x squared plus 4. Plus c, of course. I'll give you a hint. Hint. It's going to be done with a substitution. Notice what we have here. We have x squared plus 4. Cassandra, what substitution will I use? You know this. X squared plus something. You gave it to me about a half an hour ago. No. Tangent. We're going to use the tangent. When it's a plus, x squared plus, we use the tangent. So hint is let x equal 2, because this is our a squared is equal to 4, 2 times the tangent of theta. So that's the hint in order to get that result, right? So this is due Monday. It won't take you guys that long to do it. Due Monday. All right, so a little surprise, a little take-home quiz.
What was the What was the fraction that was in front of that?
For this assignment, you don't have to worry about that. The fraction for this problem that was in front of it was 3/5. But for this, I just want you to do what's in front of you right here to show this. Okay? All right. So has everybody got that? Okay. Oops. Let's make sure you guys can see it again. All right. Okay, everybody got this written down? Okay. All right. So that's what I needed to do for that very last integral there. All right, was that. So getting back here to the problem, let's just finish this off here. So this will then be, since I have a 3/5 here, this will be 3/5 times that whole result that we just have over here of 1/16, etc. Okay, because that's our coefficient in front. All right, so that problem, as we can say, was a little bit messy, right? Do we all agree that that probably was a little messy? Just a little messy, yeah. All right. Another kind of scenario you can have is this. Let's do the antiderivative of x minus 5 over x squared plus 6x plus 13 dx. Now, let's look at that denominator there. I cannot factor that denominator. Here our b is equal to 6, our a is equal to 1, and our c is equal to 13. If I look at d squared minus 4ac, I'm going to have b squared will be 36, 6 squared, minus 4 times 1 times 13. That's going to be 36 minus 52, which is less than 0. So this can't be factored from that information. So what do? If nothing in our denominator can be factored. When nothing in our denominator can be factored, we can't really use partial fractions. That's all involving things being factored in our denominator. So we can't use partial fractions. But there is something we can do besides yell for help. We can do what's called completing the square. We can complete the square in the denominator and that will provide us the help that we need. Okay, so let's see what we're talking about here. Let's just look at the denominator. My denominator is x squared plus 6x plus 13. By completing the square in the denominator, I mean getting this first part to be a perfect square trinomial and then whatever we have left over. So let's see. When we do completing the square, we take the x coefficient, which in this case is 6, and we divide by 2. So that gives us a 3. And then we have to square that number, and that gives us a 9. So I can then use that to complete the square here. My x squared plus 6x plus 13 can now be written as x squared plus 6x plus 9. That's the number I need to complete the square. But I can't change my denominator. So what's the extra number that I have to then put onto this denominator? No. 13 is what I'm starting with. Plus 4. I have a 13 in my denominator. I've added in a 9 in order to complete the square. That means I still have to add on another 4 to equal my original denominator. All right? I can't change what the original denominator is. So I add on whatever number I need to, or subtract, however it's going to work, whatever number I need to. So this denominator then can now be written like this. So x squared plus 6x plus 13 can now be written as this over here is x plus 3 times x plus 3. That's my perfect square. So it can be written as x plus 3 squared plus, I still have to add on a 4. So that's called completing the square in the denominator. So let's look at my original integral here. I have an x minus 5 in the numerator. I'm going to rewrite my denominator now with this completing the square. So my new look for my denominator is this, x plus 3 squared plus 4. In my previous one, let's go back up here. Could I do a u substitution the way this thing is written to get anywhere? I couldn't, because if I use the entire denominator for my u, I'd end up with du is equal to 2x plus 6. And that would end up, it had to be very messy to try to figure that out. This is going to be much easier. What do you think I want to have for my u now that I've got the denominator rewritten like this? Yeah, just the x plus 3. That new linear term here, that's going to be my u. So my du then becomes just dx. Now I have to replace everything here. So my denominator, x plus 3 squared plus 4, well that becomes what? U squared plus 4, right? When I substitute. Now, what am I going to do with what do I do with this x up here? What's that going to become? Well here, u is equal to x plus 3. If I subtract 3 from both sides, I get that u minus 3 is equal to x. That makes sense? So I can replace x with my u minus 3. So let's see what we get here. My x up here then is going to be replaced by u minus 3. Now I still have to take away the 5. I can't leave that out. And then my dx is replaced by du over, and now my denominator is u squared plus 4. So this has become, let's simplify, minus 3 minus 5. This is u minus 8 over u squared plus 4 du. Okay. What do I want to do to this before I start attacking it? What do I really want to do first? I have 2 terms in the numerator. Split it up. Here and here. My first term, I'm going to split it up as u over u squared plus 4 du. And then I'll split it up into negative 8 over u squared plus 4. All right. With my first one, I can do another substitution. Now, unfortunately, I've run out of letters here, but not really. Let me let w equal u squared plus 4. I'm just doing another substitution. Then dw is equal to 2u du. So this u du up here can, if I divide by 2, my u du will be replaced by 1/2 dw. So this whole integral then will become 1/2 dw times, in the middle, 1 over w. And I'll have a natural log. So it's 1/2 the natural log of absolute value of w. And, well, what is that? Back substitute, that's 1/2 the natural log of u squared plus 4. But guess what? Our original problem way back up here is in terms of x. So we have to then substitute again. We want our answer in x. So u squared plus 4, I go right up here, u squared plus 4 is this right over here, x plus 3 squared plus 4. So this finally becomes the natural log of x plus 3 squared plus 4 close the absolute value. So I had to do 2 substitutions in order to get this. What am I going to use over here where I have u squared plus 4 in the denominator? I'm going to use my tangent. So here I have my minus 8. Here my a is equal to 2. So it's minus 8 times 1 over 2 inverse tangent of u over 2, not x over 2. And then I replace what u is equal to. U way up here is equal to x plus 3. So this becomes minus 4 tan inverse of x plus 3 over 2, getting x in our answer. Right. This kind of thing here, where did this problem started here. This completing the square in the denominator is something you're going to see in homework for at least 1 or maybe 2 problems. One, completing the square like this. And you have to do it when you can't factor it. When you can't factor it, you've got to do something with it. And completing the square like this enables you to break it apart then into 2. Right. Okay, we're almost at this section is really challenging one to present, I have to admit. I want to make sure we go over this. Rationalizing substitutions. So what in the world are we talking about there? This ends up getting tied into partial fractions. Let's say we have this kind of integral where we have a radical, x plus 4, square root of x plus 4, all divided by x, dx. Okay. I'm trying to think of a u substitution that I can do here, and I tell you, nothing's panning out. All right, so that's kind of leading me nowhere. But actually, there is a u substitution that I can use, but it's not maybe obvious at all. If we have a radical like this, something like square root of x plus 4, notice it's not an x squared plus 4, so we can't use those trig substitutions, okay? Because with the trig substitutions, you have like x squared plus 9, x squared minus 16, or like that, and you can do a trig substitution. This is just x plus 4. If I let my u equal to the entire radical, let u equal x, the square root of x plus 4. That's going to work for us. All right, let's see what happens here. So let's get du. So this, of course, is x plus 4 raised to the 1/2 power. When I get the derivative, I'm going to get this. 1 over 1/2 times 1 over x plus 4 in the denominator to the 1/2 power, to the negative 1/2 power, and then times dx. Okay, but this right here in the denominator, x plus 4 to the 1/2, that's the same as my u. So I have here really du is 1 over 2 times u in the denominator dx. Everybody see that this is the same as our u, so let me get it back in there. So then I can see, well, what is dx going to be equal to? Well, if I multiply both sides by 2u, I get 2u du is equal to 1 times dx, like that. And that's what I'm going to replace my dx by, the 2u du. This is going to be replaced by u. So that's going to be u. What about that x down there? Again, I've got another x floating around here that I've got to change into something with u. Well, this is where this is a very clever thing. Notice that u is equal to the square root of x plus 4. What if I square both sides of this equation? Square. I get u squared is equal to, well, when I square a square root, I just get what's under the radical. So u squared is equal to x plus 4. So if I subtract 4, I get that I can replace x with u squared minus 4. So let's replace everything now. My square root of x plus 4 is going to be a u. My dx is going to be 2u du. And then in my denominator for x, I'm going to put u squared minus 4. So now everything's in terms of u. So let's see what this looks like. 2 times u squared over u squared minus 4. Okay. Du. Now this is, we're going to involve partial fractions, but I want to point this out. We haven't had this happen yet. Notice here, my degree of my numerator is a degree 2. It's a u squared. Also, the degree of my denominator is 2. To do partial fractions, I have to have the degree of the numerator be less than the degree of the denominator. So guess what I need to do? Good old-fashioned long division in order to get the remainder and the quotient. Long division. I'm going to use long division to rewrite this entire expression right here. Okay, so I put my u squared under that, whatever they call that thing, and to the left I have u squared minus 4. So I just divide. U squared into u squared goes only one time. And then with long division, I multiply it by these two terms. 1 times u squared is u squared. 1 times negative 4 is negative 4. Then we subtract. So what I tell my algebra class is this: change the sign. This is a plus, make it a minus. This is a minus, make it a plus. We have to subtract. If you are unfamiliar or not too familiar with long division, I suggest going onto YouTube, and you probably can find 5 million videos on long division. Okay, the u squares cancel out. Then I have a plus 4 as my remainder. So therefore, I can say this, that u squared over u squared minus 4 is the same as equals my quotient of 1, this is my quotient, plus my remainder. Well, I have a remainder here of 4. I cannot divide u squared into 4. So my remainder is 4 over what I'm dividing by. So that's how I was able to rewrite my original expression. Now I can integrate this. So we have u squared over u squared minus 4 du. I can rewrite it just from having used the long division as 1, that's my first term, plus my second term is 4 over u squared minus 4. Oh, did I leave out the 2? Thank you. Thank you, thank you. Yep, let's put the 2 right in front like that. Yep. All right. Okay, well, the first term we can integrate, it's just a 1. It's going to be turned into my u, right? So my first term is going to be 2u, but keeping that u in there. Now, this one here, I can use partial fractions. In fact, we already did one very similar to this. Let's go down here, 4 over u squared minus 4. Now we have the degree of the top is 0 rather. Degree of the bottom is 2. We can do partial fractions because we know that this factors as u plus 2. It's the difference of two squares, u plus 2. And the other factor is u minus 2. And I just put the a and the b up above them. And so I can solve for the a and b. Now, we multiply both sides by, again, we multiply both sides by u plus 2 times u minus 2, the factoring of the denominator. And then I'm just going to tell you what we get because this is fairly straightforward. We're going to get that a is equal to negative 2 and b is equal to positive 2 when we figure that out. This is a very straightforward one. So therefore, this second part here, 4 over u squared minus 4, du, is going to separate out as minus 2 over u, let's see, a is minus 2, minus 2 over u plus 2, and then the b is 2 plus 2 over u minus 2 du. All right. Both of those are natural log. Minus 2 natural log of u plus 2 plus 2 natural log of u minus 2. I think, let's see now, where, yes, we are still going to have a 2 in front here. Yep. Wait a minute. 2 times this, 2 times this, yes. So we still have, yeah, here it is right up here. 2 times this. So thank you, Cassandra. We're still, I don't want to drop my 2. All right. So let's keep the 2 there. And so that's going to be minus 4 natural log plus 4 ln of the other one. Okay. So that'll work. So then I have to get x back in my answer. So that's going to be minus 4 natural log of, now u, what was u originally? Well, originally, remember, u was equal to the square root of x plus 4. So now I have u plus 2. So that's going to be the square root of x plus 4. And then outside the radical, I just tack on the plus 2. And then plus 4 natural log of, again, my u was the square root of x plus 4. But this time now, outside the radical, I put a minus 2. And then let's not forget that very, very first term that I did. What was that? That was 2u. And of course, 2u is going to become 2 times u is the square root of x plus 4. So this right here plus the c, that is my antiderivative. minus 4. All right. 2H. Oh, you know what? I just realized something. When I did this on my paper here, and I just told you that A is equal to minus 2 and plus 2, that was already with multiplying the 2 by the 4. So sorry here. This, I had in my paper, I had already multiplied 2 by the 4, and I got an 8. And that gave me my A equal minus 2, and my A equal minus 2, and my B is equal to plus 2. So I'm sorry. So way down here, this then, I need to get rid of that other 2 here. That's already been taken care of. And so, what do I have? So I have, this should be, such a mess. That should be minus 2, and that should be plus 2. I had already taken that into account. Sorry about that. So that should be minus 2, and that should be plus 2. And why did I? All right, I guess I know we're over. Well, we start 6 minutes late anyway. The moral of this story is this. When we have a radical like something like the square root of x plus 4 here, use that as your u. That'll frequently work out as your u substitution. You've got to get everything in terms of u. And then oftentimes you can do the partial fraction to decompose it and then get your antiderivative. Okay. Thanks. Not a peep out of those high schoolers today. Not a peep. Not even a hello. Tired. I don't know what's going on over there.
What happens if their schedule fluctuates?
I try to record everything, although a couple of the recent recordings have not been successful.
Because sometimes there's half days on Friday.
Well, actually, they kind of do have to. Wait a minute.
What?
Rockwood doesn't even have.
There's going to be one day, I think it's November the 1st, when you're going to get to see all of them, and they're going to get to see you, because they're going to be here, because they're off completely. There's no school there. So they're supposed to come here on that day. There are other days where they have limited schedules, but the guys said that shouldn't be a problem for them. They should be able to.
I guess they got it figured out.
Yeah, right. Except for
a day or two in here would be a
it's disastrous. Except for that one day where they're supposed to be here. Yeah.
November what?
Thursday.
Because there's that day where they get off to the parent-teacher conferences, and that's usually the
That,
Friday.
yeah, I don't know if that's November 1 or what, but yeah, it's something like that.
Sounds awful.
Let me do something here, Carl.
What?
I got to stop the recording. Okay. And I got to do something else here. Let's see. Where's my P file? P file, oh, there it is. P file? Maybe, Joe, you can help me with something, and just since you are here anyway, after you get finished with that. Oh, thanks. I was going to get to that. Thank you, though.
It actually just turned out I just want to get things ready for Monday.
Okay.
So I seen that your class was over, and I was just like,
Yeah. Harold, did you have a question? No?
No.
All right. Well, okay. Well, I hope you're feeling better. I am. Okay, good.
Well, where should I
Give me a minute. Oh, here, up here. This is something that's happened that's new in the last week. Normally, when I save my recording, previously it had always come up to the P drive, P://scans, backslash.
Mm-hmm.
Now it's coming up to the C drive.
Oh, that's not good.
I know, because the C drive, we all know, could be miraculously erased.
Exactly.
So, and then I'm coming back here, down here, and is this an X here by what is the P drive?
You just click on it and expand it out.
Oh,
It just didn't do it there right away.
oh, okay, so let me just do this, P scans. Oh, wait a minute. Okay, oh, I gotta do okay here. Okay. Well, I just want, it's just another little odd thing that,
Yeah. So, I mean, all these odd things, just go ahead.
yes, well,
Send it in.
no, this isn't that.